Hi everyone, this is going to be an overview of the Organic Chemistry 2, and we are going to review the labs. So I'm going to go ahead and share the screen here of our first experiment, which is going to be infrared IR spectroscopy and NMR. So with regards to reviewing the lab manual, make sure that you understand the back theory behind it. I'm not going to overview everything. The main thing that I saw looking through here that I wanted to point out was that the relative intensity of absorbance that is proportional to the change in the dipole moment for motion is relative to, if you were looking at, for instance, here, a carbonyl stretch versus an alkene stretch. So dipole moment can cause many deep peaks or troughs within the IR spectra. This can be seen as well in the hydroxyl groups and as well as some aromatic groups. So one big thing is to understand the differences between the types of stretching. So there's symmetric stretching, asymmetric stretching, scissor bending, and then rocking motion. And these are common types of themes of modes of CH2 vibration in this case, but this is also just the types of modes that you will see within the IR spectra for various types. And the best thing to do for IR spectra is to memorize the most important functional groups. So that way that you know the difference between if you have an oxidation or reduction reaction and you need to compare the two together, then you would know exactly where to look. So for instance, here is a very good table, 11.1. This is a good one to review because it can show you, for instance, halogens here, 3600 to 2700, hydrogen bonded, and this is very prominent, or ammonium bonding. But of course, the hydroxyl bonding you can see with a very broad shift from 3300 to 2500. Then as well, the alkynes or nitriles or these sort of double bonded nitrogen carbon oxygen groups. These are commonly found from 2400 to 2000. And then your double bonds, like the sorts of ketones or aldehydes and carboxylic acids, they'll be between 1850 to 1550. And then finally, your single bonds bending or stretching from 1600 to 650. And especially within the 1850 to 1550 region, it is important for you to know the difference between the aldehyde, the ketone, and the carboxylic acid. Those carbonyls are very different in numbers, and we'll be seeing that as we go down further. So I'm not going to be going too deep into the action of taking IR spectroscopy, and if you need a more in-depth review of that, make sure to watch the video I had posted before. But I primarily wanted to come over here to the table and see the very important things that would be needed to be memorized. So when we look at some of the sort of ketone-esque carbonyl ones like carboxylic acid, aldehydes, and also our ketones, you would note that there are also some higher energy levels here that you can see, but the most important ones are going to actually be in the 1700 to 1800 range. And so, for instance, here, aldehydes, ketones, 1680 to 1740. That's important to note. And it looks like on this table, they currently do not have the other forms of carboxylic acid, etc. But I will try and find that if we can't within this document. But the take-home message here would be to review down here in these sections, so alkanes, to see a stretch in 3000 to 2800. And remember, it's not going to be too deep because it's not a strong dipole moment, but there are some major bending modes from 1470 to 1420 and 1340 to 1380. And then additionally, as they say, the stretching in 1300 to 1100. Then going into alkenes, we remember that it actually moves further up the chart. So instead of it being 3000 to 2800, it's now over at 3100 to 3000. And additionally, you'll have bending and out of plane vibrations in the 1000 to 650 region, and the carbon-carbon alkene stretching in 1600 to 1675. So this can be seen as a much different location than the alkanes, and you can also notice that everything is starting to get shifted more upfield into larger wave numbers. And so finally going to alkynes, you can see it is around 3300. So in a way to remember this, you'll remember that alkynes are the highest, and then it goes to alkenes and then alkanes, and those sorts of shifts occur across. So like the stretching band here is 2150 to 2100 versus where we had our stretching all the way down at 1600 for the alkenes. Additionally, if an alkyne is monosubstituted, that's where it would be. But if it's disubstituted, it actually would be even higher energy level at 2270 to 2150. Then going forward, this one is a particular part of talking about the polarizing substituent with an alcohol nearby with a partial peak at 1600. And I wouldn't work too hard to memorize that as much, as it would be better to memorize that the alkynes are the highest energy level shifted going into the alkenes, and then the alkanes is the lower energy levels. So then the aromatic rings are particular because they are going to be within that same region. Now the 3100 to 30,000 region, like kind of near alkenes, near alkane, but it would be very significant. And unfortunately, this doesn't show it here, but I will show an example later for an aromatic ring so you can see exactly how that looks. And another portion of it would be noted that the out-of-plane bending from 900 to 690 and some sharp peaks at around 1600 and 1500. So primarily with the aromatics, and here you can see that there's a nice little dip here in the 3000s, but it's kind of clouded because of the issue is that we have our phenol here. And this is a very big, they call it a very deep and broad trough for the hydroxyl group that appears in the 3000 to 4000 range. So they would say that in this instance, they say around 3,650 to 3,600. However, it can vary between 3,000 to 4,000. And usually you'll see a very, very deep and broad trough there because the hydroxyl group is so polar. There's such a strong dipole moment of the electron energy going towards it. So that is the reason that it would be such a deep trough. And additionally, whenever you look at things like ketones or any carbonyl groups, they will have those deep troughs as a very noted situation. So when we look at any other sorts of bonds, you can see that the CO stretching, it would be around 1500 to 1300 and 1220 to 1000. Those are important as well. But again, when you're looking at these kind of things, some of the things can overlap when you get close to the fingerprint region. So it's really more important for you to remember the strong functional groups such as alcohols, triple bonds, double bonds, carbonyls, amines. And now speaking of the carbonyls, now this is the really important thing because this is going to be kind of hard to understand when you're looking at a sheet and you see an IR spectra of what kind of carbonyl you're going to be looking at. So it's important to try and remember the relative range. So the carbonyl, the C double bond O stretching frequency of saturated aldehyde and acyclic ketones will be from 1735 to 1710. So that's the aldehyde. And then 1725 to 1700 for the ketone. So the aldehyde is a little higher, the ketone's a little bit lower, and that's the main thing to remember, but they're very close. So it's going to be a little hard for you to really know exactly where that is unless you know the exact location of where this should be. So in the instance that you have an aryl aldehyde around 1700 to 1690, or diaryl ketone would be at 1670 to 1660. Now here is an interesting point. If you were looking at it, if somebody said to you, I have a carbonyl compound, is it a aldehyde or a ketone? Then one important thing is that you can actually look around 2850 to 2700 and you would see two peaks, because that would be the carbon-hydrogen stretching vibration. So this is one important thing to remember when you are comparing carbonyls or if you're trying to identify an unknown spectra. Additionally, another thing that is not as common, but it is a situation that you may look at, because within a cyclic ketone, such as the isoboronol that we had looked at, this would be an instance where you would see 1780 to 1745 inverse centimeters. And that would be important because that is an almost 100 centimeter shift from the relative normal ketone or aldehyde. So if you do end up having sort of cyclic ketone, remember to look a little closer to 1800 and you'll see a good sharp peak there because of how polar the system is. Finally, for the carboxylic acids, you'll of course see your hydroxyl group, and that'll be a large indicator to you. The first indicator that you see with that broad peak over in the 3,300 to 2,500, see, and it's a very large range. So you would definitely notice it if it was very deep trough. But then also you would see the carbonyl group with aliphatic acids to be at 1730 to 1700. Or if it has alpha unsaturation, which would mean on the carbon next to it, it has a double bond, it would actually shift slightly downfield a little to 1720 to 1680. But the main thing with carbonyls is to notice that you have a carbonyl peak, so a very sharp peak at the 1700, the lower 1700, upper 1600 region. And then you would also have to see the hydroxyl broad peak over in the 3000 section. So if you did see a carbonyl peak in an IR spectra, and then you also saw the hydroxyl peak, that would be indicators for you to say, okay, I don't have a ketone or aldehyde, I actually have a carboxylic acid because of that hydroxyl group. So make sure to denote the things in your mind that will allow you to separate these sorts of carbonyl compounds because they are very similar in location due to that carbon-oxygen double bond. So going forward, as you can see here is a good example of that OH stretch, and then some other little key indicators that you can find among there. But make sure to understand the main things that will actually separate them from each other. So going into the final carbonyl that we have, that would be a carboxylic ester, which would be a carbon bound to the acid portion of a carboxylic acid. Now this will be a little higher in the 1750 to 1730 range. And if you do have unsaturation adjacent, which would mean the carbonyl group, the alpha to the carbonyl group that you have a double bond, it'll lower it by 10 to 15 centimeters. But if you have unsaturation next to the oxygen, so on that carboxylic acid oxygen, then you have a carbon coming off. If that alpha or beta has double bond to it, then it increases the frequency by 20 to 30 centimeters. So you will either see it down closer to 1700 or shifted up closer to 1800. The esters are a little particular with regards to that, so it would be important for you to denote the lack of a alcohol group. That would be one indicator that you have an ester. And then additionally, you would want to see this one would be a big indicator, would be this carbon-oxygen carbon bond, and it will be appearing as two bands in the 1280 to 1050 inverse centimeter. And that is going to be the indicator for you because you would notice the carbonyl peak. However, you would not see the hydroxyl group, so you would be wanting to look close to the fingerprint for the carbon-oxygen carbon stretching of the ester bonds. And then there would be additionally an asymmetric stretching peak that's strong from 1280 to 1150. And then going over into cyclic esters, which would be lactones or any other sort of five-membered rings, which would be a gamma lactone. They would absorb around 1770, so it's going to be shifted up. And then beta lactones would be even further up, which would be 1820 inverse centimeters. So these are going to be some particular ones that may or may not be brought up on the exam with regards to the lactones, but I definitely would still denote in your head where the ester peaks would be located for that carbon-oxygen carbon stretching. So a big one as well would be the acid anhydrides. And the main thing to understand here is that you're going to have two high-frequency carbonyl absorptions, and that would be above 1800. So this is unique because most of them only get near 1800. This is going to be one that's going to be between 1830 to 1800. And then as well as secondary one that would be 1775 to 1740. So you'll see two high frequency peaks that would be shifted higher energy level in the carbonyl area, because most carbonyls are closer to 1700, some of them in the upper 1600s. But this will be very clear to see when you have two deep peaks within the lower 1800s and the high 1700 area. So going into amides, make sure to know that the amide carbonyl stretching is actually lower. So this is going to be quite lower relative to the other carbonyl compounds, which would be between 1700 to 1630 inverse centimeter. Now remember, again, this has a pretty strong dipole moment. So that's going to actually end up being a pretty deep peak, just as they said from the start as well. But additionally, if it has adjacent unsaturation or lactams, which would be a ring involving the amide, then it would cause the absorption to shift to higher frequencies. And so primary and secondary amines, This is another good indicator. If you just have an open amine, whether that be primary or secondary, that would show nitrogen hydrogen stretching around 3500 to 3100, and you would see bending between 1640 to 1550. So mainly the big one there that would be good to remember would be the 3500 to 3100 area, and then we'll discuss that further going down to the amines. But moving over to ethers, not to be confused with esters, but ethers, which would be, for instance, diethyl ether, would be an oxygen bound to 2 carbons, and you would find asymmetric carbon-oxygen stretching around 1280 to 1050. So remember, these are more of the carbon bonds and carbon-oxygen bonds, so it's going to be shifted way more upfield, close to the fingerprint region. And additionally, with phenols and enol ethers, they're going to absorb around 1275 to 1200, and dialkyl ethers at 1150 to 1050. However, epoxides, you're going to have 3 characteristic absorptions. So if you maybe by chance you have it, you would see it around the lower 1200s, lower to mid 1200, the 950 to 810, and 850 to 750. And in those last ones, the fingerprint region is going to be ambiguous as always, because especially if you have multiple compounds in your mixture, it's going to be hard for you to see that end. So try and look around closer to the mid 1200s for that first part, and then you can correlate the rest of between the 950 to 810 and 850 to 750 if it's available for you to accurately inspect, because as you can see here, it starts to drop off near IR. And so going into amines, primary and secondary show the innate stretching like we discussed in 3500 to 3300. However, primary amines generally have 2 bands that are approximately 70 inverse centimeters, so almost 100 inverse centimeter apart, because of their asymmetric and symmetric stretching. So you can see here, there's actually 2 peaks that go down, and that would be the asymmetric and symmetric stretching. And the intensities are less because it is less electronegative as relative to hydroxyl group, because oxygen is more electronegative than nitrogen. So that's the reason you wouldn't see as broad of a peak or as deep. So you would notice these little dimples in a sense on the 3300 to 3500 region with 2 peaks for a primary amine because of the 2 asymmetric and symmetric modes of stretching. So additionally, it should be noted that the nitrogen-hydrogen bending and carbon-nitrogen stretching are not as strong, and they can occur at around 100 inverse centimeter higher frequencies if you do have those bonds. But there also is another broad band over from 900 to 700 inverse centimeters from the out-of-plane bending of the amine group. And again, the fingerprint region is a little bit ambiguous to look at. So primarily you would want to find more of the common ones, such as in the 3,300 to 3,500 inverse centimeter range. So for the last 2 for today are going to be the nitro group. And this is a very strong stretch because it is extremely polar. Nitrogen-oxygen bond is very polar in a nitro bond. So you're going to find that by asymmetric stretching in the 1560 to 1520 inverse centimeter region, and then also the symmetric stretching at 1360 to 1320 inverse centimeter region. And those are that's just going to be the area that you're going to want to remember, because it's going to be extremely strong, extremely deep, very strong dipole moment. So at 1560 to 1520 and 1360 to 1320 inverse centimeters, you'll find the 2 strong peaks there. So finally, nitriles. This one's very simple to remember because it's one of the most obvious in this region, which would be 2260 to 2220, and that would be a very sharp, strong absorption of the nitrile. So please go forward to review the sample preparation part if you need to. It's fairly straightforward and simple of how you have your sample attached into your salt plate or into a holder, or utilizing the NuJOL method. But additionally, do remember that certain parts of that, such as the NuJOL, will be a little bit disadvantageous because of the locations of the NuJOL functional groups. And additionally, make sure to go forward and review all of your post-lab questions that were completed here. And then, everyone did really well with regards to analyzing their information, but if you do have any questions and need any guidance with regards to your post-lab questions, please let me know before the final. And then additionally, now we're going to go over into the NMR. So the NMR background information, I'll let you review more into that video because I saw that everyone in the class had already watched over that video. So the primary thing that I really wanted to discuss with NMR was going to be the location of most of the functional groups. And so I'm going to pause this for one moment and open up a separate sheet. Okay, I'm going to share this table here. And so on this table, and you can utilize any sort of common IR, proton, NMR, chemical shift sheet, but this is a good sheet because it's going to describe to you the locations of the common groups. And this is the most important part of NMR, is to understand where the location is of the groups and the quantities and the adjacent carbon-bound hydrogens, so that way that you can know whether you have singlet, doublet, triplet, multiplets. And the primary thing to take from here is to remember the big noted things, okay? So over here to start, extremely downfield, would be the carboxylic acid, and that's going to be around 11 to 10. Very, very staunch. Very easy to note that because of how far up it is, okay? Then secondly, near 10, we would have our aldehyde. So that's a good location for you to remember the carbonyls up here. And then ketones, however, they're not going to be in this location because they don't have as far downfield shifted hydrogens. So we'll go farther into that soon. Now, ranging all the way up to near 10, a little past 9, and all the way down to 5, you're going to find amides. Now, this is not to be mistaken with amines. This is for amides. Now, within the, I would say, upper 6 to mid 7, you will find all of your aromatics. This is a very, very key location for aromatic groups, and you will always see them in between that 6 to 8 region. Then for a phenolic hydrogen, you would find that anywhere between from the mid 4s to the lower 7 in it, and that would be additionally because of the aromatic hydrogens shifting this. So as well, you should note that the hydrogens that are adjacent to the hydrogen that you are reviewing will cause it either to shift upfield or downfield, and that will cause the location of your chemical shift to be different for each individual proton. And so here we have our alkene proton that we noted between 5 and 6. So that's pretty easy to denote in your head because the location is right in the middle of the chart. Then if we have an ether right here, it's going to be at the upper 3s, lower 4. And additionally, if you can locate this sort of aniline, which would just be an amine bound to an aromatic compound, those hydrogens will be found in between the mid 2s to the lower 5s. But if you have a primary secondary amine, then it's actually going to be really far upfield, closer to between 1 and 3. Any sort of primary secondary alcohol, you're going to find between 1 and 4.5. And then if you have anything sort of like toluene or any sort of carbon with hydrogens bound to an aromatic compound, and this is toluene right here as an example, it'd be in the around 2 to 3 range. There's a very particular little location. This can also be denoted as alpha carbons to double bonds, or also here's our ketone. So the ketones as well are going to be all the way down here because they're just so shifted up there because of the fact that it is farther away from the carbonyl group itself, versus where you have your aldehyde directly bound to your carbonyl carbon and your hydroxyl group bound to the carbonyl. However, hydroxyls are more commonly found in the higher end with regards to the dipole moment, especially on the carboxylic acid here. And then finally, if you do have any sort of free-floating hydrogen that's just bound to an alkane, it's going to be extremely low. So the alkane will be over here around the lower point up to 1 and near 2. And then here are the common groups that you would see as well. So as they say here, alkyl shift would be around 0.9. Now an alkyl that's next to a methylene would be 1.3. So you see it shifts it because of the adjacent carbon. and the hydrogens that are in between there. And then if you have a methane right here, so that would be a carbon that is tri-substituted, and then this hydrogen that's bound to it, it's actually going to be shifting more downfield. So as we get more substitution, it becomes more and more downfield. And then an allylic carbon, like we had discussed, it's up in the upper ones, lower twos. The alkenes will have between 2 to 2.3. An aryl carbon with bound hydrogens, or benzylic as they call something like toluene that we discussed, near 2.3. An alkenyl, so this is actually where the triple bonds will be, is around 2.5. Between 2 to 3, you're going to have alpha carbons to a nitrogen. So if you have a nitrogen that has a carbon bound to it with hydrogens and you want to know where that is, it's around 2 to 3. If you have an alpha to a halogen, so if you have a chlorine bound to the side and you have a carbon here in between an R group of whatever and then your halogen on the side, you would actually have it between 2 to 4 for the hydrogens there. So the halogens shifting the hydrogens more downfield. Then if you have your ether here, you're going to be looking at closer to 4, 3.8, so alpha to oxygen. If you have a fluorine group by chance, it actually shifts it very far downfield. So the more electronegative, the more we're shifting downfield and going further towards that. Then we have our alkenes, which will be between 5 to 5.3. And then our aryl or aromatic hydrogens, like we discussed, between the lower 6 to the upper 7s. And that is a very key location for all aromatics. Finally, the aldehyde, like we discussed, near 9.7. And then a couple of the important ones from the oxygen and nitrogen groups would be over here. The alcohol, and it has a very wide range between 0 and 5. The phenol, between 4 and 7. Carboxylic acid, extremely downfield, 10 to 13. Amines, extremely upfield, between 0 to 5. Your aniline group, that would be between 3 to 5. And then finally the amides, which would be right in the middle between 5 to 9. So if you do want to review this, you can always just go forward to Google the proton NMR chemical shifts, but the people who kindly provided this for us would be the California State Polytechnic University in Panama. And this is the sheet that I'm going to use to, allow you to have a review set for this. And it is important for you to remember where these locations would be, because I would expect on the final for them to provide you with some chemical shifts and then ask you to say, which functional groups are these? And so it would be important for you to try and remember the relative range, and especially the most important ones that would be extremely out of place, such as the carboxylic acid and aldehydes, or even all the way up to just the alkane groups at the start. So I'm going to pause the video right here and then switch over from the NMR section into our next experiment. Okay, so now that we're going into our second experiment here, which would be the reduction of 9-fluorinone. So remember that reduction reactions, they need to involve a reducing agent, whether it be weak or strong. In this case, sodium borohydride is a mild or weak reducing agent, and it does work on ketones. However, if we were trying to go forward with something like a carboxylic acid, we would want something stronger like lithium aluminum hydride or Dibol. And so the primary thing that I want to do, since we have the reaction right in front of us, is actually switch my screen over to having the mechanism presented for us, because it's very simple for me to just tell you that 9-fluorinone is reduced by sodium borohydride in the presence of alcohol, and then you finally get your 9-hydroxyfluorine. But to actually provide you with a better source of information, I would rather go ahead and have us switch over to the reduction. So let me pull up the image here. All right, so it's a very simple mechanism, okay? So there are just gonna be 3 steps in here, and we're gonna go step by step very slowly, okay? So firstly, sodium borohydride. So remember, hydride is not the same as a proton. A hydride is actually a hydrogen with a negative charge on it, and it can actually act as a nucleophile. So what's going to happen is the electrons that are bound from between the boron and the hydride, the electrons are going to come out of the boron and donate to the hydride, okay? Then the hydride is simultaneously going to attack the carbonyl carbon because it is electrophilic. Then the pi bond is going to break here, and the electrons are going to donate up to the oxygen, causing it to have a negative localized charge. And then what we can do is that we can just perform a workup involving either water or light acid in order to protonate our alcohol and leave us with our 9-fluoronol. And it's a very straightforward reaction. So all that you need to remember here is that the hydride is the actual nucleophile, and that the carbonyl carbon is going to be the electrophile, followed by the electrons going and the pi bond breaking, the electrons moving up to the oxygen, and then final quenching with acid or water. And that's going to be all that you need to remember for this portion. I'm going to switch my share back over to the lab manual. And the main thing to additionally remember is to go through and note the locations within here. So for instance, the IR spectra, make sure that you note the differences between the carbonyl ketone and the hydroxyl group. That'll be a big one there. Another thing you can do is review what it would look like on an NMR spectra. So look at 2 NMR spectras of 9-fluoronone and of 9-hydroxyfluorine, okay? And then finally, make sure to review the other portions of this post-lab questions, and then that will be the main portion of this experiment. Okay, so for this experiment on the oxidation of isobornol, we're going to be doing the opposite of what we did last time. So instead of performing the reduction in this case, we're going to be performing oxidation, which would be noted that we can additionally use something such as KMnO4 potassium permanganate or a hexavalent chromium. And then additionally, in this lab, we're going to actually be using hypochlorous acid that would be from the reaction of acetic acid and sodium hypochlorite in order to oxidize our isobornol. And so just as like the other experiment, I wanted to come over and switch the share screen to here so I can discuss the reaction mechanism for you. It's pretty straightforward. So what we actually are going to go for to do is provided by an E2 elimination. So what's going to happen here is that we're going to go in and we're going to take the chlorine, and it's going to actually come in and bind over to this oxygen here and give off a proton, okay? Then the oxygen electrons from water can come in and take off this hydrogen adjacent. And simultaneously, the electrons can come over from the hydrogen, bind to the oxygen in order to create a ketone, and then kick off the chlorine as a good leaving group. So just remember that this reaction is an E2 elimination. The main action, firstly, is that the hypochlorous acid will act and allow the chlorine to come in and bind onto the oxygen, followed by the water's deprotonation here to donate the electrons up and create the ketone and give off the chlorine. So coming back over to our lab manual, you want to see here to make sure to know the relative IR spectra that would be from the starting material, the isobornol, and then CAMphor, the product, the ketone, so know the differences between the alcohol and the ketone. And additionally, come down and review your post-lab questions and make sure that you understand how to look at the oxidation numbers with regards to oxidating or reducing any of these sort of products. Okay, so for this experiment that deals all the reaction of anthracene with malic anhydride, we should know that this kind of reaction is called a cycloaddition, and it involves 3 pi bonds, 2 of them from the diene and 1 from the dienophile. So in total, this would be counted as 4 pi electrons and 2 pi electrons adding together. So we would call it a 4+2 cycloaddition. This can be denoted from any sort of reaction that has specific quantity of pi electrons that are involved, and there are other cycloadditions that have larger or smaller quantities. So normal deals, all their reactions are favored by electron donating groups on the diene, which is on the left here, 2 pi bonds, and the electron withdrawing groups on the dienophile, the 1 pi bond that's going to be, reacted with. And we can look at a chart after this that'll show electron donating groups and electron withdrawing groups that can commonly be found on dienes and dienophiles. And so this is the basic schema, and I'll show you the reaction in another screen here shortly. But we would go 1, 2, 3, 4, add it to 5, 6, and then that makes the full ring, and that's the way that you should number things whenever you do perform these reactions, so that way you can see the addition scheme. So in a sense, the pi bond here rotates over to create this new double bond. This pi bond rotates over to create a new sigma bond, and then this pi bond rotates over to create a new sigma bond between 6, 1, 4, 5, and then the new double bond between 2, 3. And so this is the basic schema, but I want to switch over to look at the mechanism pathway. And it'll be the same sort of mechanism as these sort of folding curved arrows. So let me switch my screen over to here. So these are going to be your electron donating groups or activating. And this would be noted as a deuterotonated hydroxyl group, an amine or a dimethylamine, hydroxyl, an ester, the nitrogen of an amide, the oxygen of an ester, a halogen, and then you would go over down into your electron withdrawing groups. So like we had seen there, we can go ahead and have either carboxylic acid carbonyl or carboxylic ester, a halide here on a carbonyl, or an aldehyde. Any of these groups here would be good on the dienophile, and the diene would want something that's activating. And so in the case that we come back over to our lab manual to note, like we had said, that the donating groups on the diene, so the donating groups would be the resonance in between all of the aromatic compounds here. And then the withdrawing groups, the electron withdrawing groups on the dienophile, would be these carbonyl ketones here in this case. And those would be pulling electron density away. And so we want to look and see how that we're going to perform this reaction. So let me switch over to here, close this one, and then, so here, this is how we're going to do. It's going to be the 4+2 reaction schema like before. So instead of the electrons being on the other side, we're going to start from here. So this double bond is going to create a sigma bond from this carbon here to this. This double bond is going to break and create a sigma bond to the carbon across from it. So it's going to create a bridge system. And then this double bond is going to actually bond over to create this aromatic ring here and stabilize that. So you get your aromatic ring on the right, the aromatic ring on the left is still the same, and then you have your bridge heterocycle now with your malic anhydride on top and the double bond broken to just have a single sigma bond there. So just remember that this pi bond breaks to create a sigma bond, this pi bond breaks to create a sigma bond to create this bridge heterocyclic system, and then finally this pi bond shifts over in order to create our aromatic ring here. And so now we're going to switch over here, and I'm going to pause it for one moment to switch over to the next lesson. Additionally, before I switch over, I wanted to state to remember to review the data analysis here and to make sure that you comprehend how to perform the Diels-Alder cycloaddition reaction. It's very straightforward. You just need to make sure that you rotate the compounds correctly, understand the diene and the dienophile, and then as well to make sure that if you need to review any sort of IR or NMR spectroscopy with it, to make sure to go forward and look at some of those examples on Google so that way that you can know where to look for the changes. And now I'm going to be switching over to the next lesson. Okay, so electrophilic aromatic substitution is a common mechanism that is known from the nitration of bromobenzene or any sort of electrophilic aromatic substitution onto an aromatic ring. So an arene reacting with an electrophile will cause it to be a substituted arene, which is the aromatic ring itself. Here is the common schema, the formation of an electrophile, the reaction with it, and then the loss of proton to receive your product. So in the case of the nitration of bromobenzene, we need to note that one big thing to remember is that you can get any form of it in the sense that you can get your ortho, your para, or your meta. And you should know which one is more favorable within the lesson here. And the main thing that I wanted to show from this reaction is the scheme on not only how to nitrate it, but how to get your nitronium prior to that. So going forward, make sure to review down here with regards to the reasoning of why we can create our other substituted nitrobromobenzenes and how we would actually isolate it. And in that sense, I would also recommend to review the reaction videos within your Canvas portal so that way that you can see the precipitation occurring of your nitrobromobenzene. So going down here, just to let you know, of course, there was no post-lab here, so make sure that you can go forward to review an IR spectra and see the difference between a bromobenzene and then a nitrobromobenzene on the IR spectra. Additionally, I could also recommend you to look at NMR spectra. It would be a little bit helpful just because you would see the loss of a proton. But again, the nitro group is not any sort of proton, so you wouldn't see that on a common proton NMR. But the main thing I wanted to show everyone today with regards to that, and I know this is a little lower quality, but I'm going to go ahead and explain through it with this photo as an example. So the nitric acid with the sulfuric acid in the environment, what can happen is that the nitric acid can actually take the proton from the sulfuric acid and then make it protonated. So when that alcohol on the nitric acid is protonated, it acts as water in a sense and will want to leave because it's very stable. So this oxygen with a negative charge wants to become stabilized and will actually donate its electrons down to create its double bond and give off that water. So once the water is left into the system, you are left with your nitronium ion. And this is the main part that you just need to remember, is that the sulfuric acid will protonate your nitric acid, allowing it to become the nitronium ion. Then the double bond can actually attack the nitronium, and then you will be left with an intermediate of your nitrobenzene. So then the proton, the last step of this reaction is the leaving of the proton and donation of the electrons in order to recreate your aromatic group. So once again, they show here the benzene ring attacking the nitro group, it rotating out its electrons to the oxygen, and then the simultaneous protons donating the electrons back in order to create your happy benzene ring. So I'm going to now switch over here to this one so that way you can see the schema, because now you know how to create the nitronium from the protonation by sulfuric acid. So then you have your bromobenzene here. And these are the three mechanism pathways that you can see for it to be either ortho, meta, or para attack. And so as you see, the double bond here attacks the nitronium, and then you're left with the carbocation on here. And so it can actually rotate through by resonance, and that was drawn by you in your post-lab notebook. I had seen on everyone's post-lab notebook. You did very well. So the main thing is just to know how this resonance can occur throughout. And then finally, the deprotonation by the proton donating its electrons back to the ring, and then leaving you with your benzene ring and your bromonitrobenzene. And so this is just primarily I wanted to show you that the double bond is performing the attack and that the nitro group is binding to whichever preferred spot is good for it. So in the case that we know that ortho-para is preferred, just don't forget that meta can occur. It's just not as favorable. And so since now that you've seen this mechanism here, just make sure to review through your post-lab notebook and to memorize this mechanism, since it's very straightforward, between the protonation from sulfuric acid onto nitric acid to create the nitronium, and then finally the nitronium to be attacked by the ring and then substituted by nitro group, and then the subsequent loss of the proton and donation of the electrons to recreate that aromatic ring. So now I'm going to switch back over and pause this for a moment, and then we're going to go forward into our next lesson. Okay, so for here, with regards to our polymerization nylon experiment, I wanted to go down here to mainly tackle the primary concept here, and that's the formation with this condensation reaction. So chain reaction polymerization, or cationic polymerization, in this case, is going to be down here. Let me see. So in this case here, they discussed it, however, they didn't actually place it here. So let me see if I can have a better example of our chain growth. So I'm going to pull up a separate document for the chain growth, but we're going to go ahead and talk about the step growth here firstly, and then I'm going to switch over to our chain growth. So the step growth polymerization is the reaction between two different difunctionalized monomers. So in an example, we're going to use a diacid like terephthalic acid in reaction with a diol, such as ethylene glycol. So terephthalic acid with ethylene glycol will go ahead and bind onto here, in this case of the step growth polymerization. And just remember it as steps, as in that it binds onto the ethylene glycol and then goes on to the next step and then adds to the acid on the glycol side. and then the phthalic acid will bind onto the side of the glycol, and then it'll continue to go forward in step by step. So it'll be the acid, the glycol, then the acid, and then the glycol. And all of these are going to be very simple condensation reactions. So all you do is just cleave the chain with the carboxylic acid group there. You cleave off the hydrogen, and then the oxygen will bind over to it. You'll create that, and then you'll be left with water on the side. So that is the main portion here. And so, as they say, partially here is chain growth is initiated. The acid catalyzed reaction of a carboxyl group of the diacid with hydroxy function to the diol to provide an ester. So the glycol is creating an ester. You have water leaving the system, and then you continue to grow it further by adding more acid and glycol to it. Now, it is one main thing to remember is that step growth polymerization process is slower than the chain reaction processes because they have higher activation energies. And so another portion, and primarily what we need to review with regards to what we did, was the polyamides creation by a step growth process by the reaction of a diacid and diamines. So instead of us creating our acids, our new carboxylic esters, we're going to be creating carbamides. So in this case, the amides that are created are going to be the cleaving of this OH on there, and then the nitrogen's binding to the carbonyl because it's going to be acting as an attacking group, and then one proton of the amine and then the hydroxyl group are going to leave. So water is always leaving, no matter whether it's an amine and carboxylic acid reaction or carboxylic acid and an ester reaction. The main thing here is that the amine binds in, a proton of it leaves, and the hydroxyl group of the carboxylic acid group leaves, creating water on the side, and then you have your amide bond there. And then in the same fashion, then your acid will bind over to the next portion of the amide, and then the amine will bind over to create the amide on the next portion of the acid. So just remember in the step growth pattern, in the same sense as the chain growth, it is continuing to add in, and that it requires more of like a catalyst in a sense. That's why we used partially some of the base in order to initiate this reaction. And this is the 6,6 reaction, but of course, remember that the 6,10 reaction is the same thing. We're just using a different chain base. So in this case, decane dioic acid, which is the 10 carbon portion, and the 1,6-hexene diamine is going to be the 6 portion. So just remember that this can be created, or additionally, you can use decane diol dichloride. And in this case, what you would create on the side, since so you're pulling off the chlorine, and additionally, the amine is attacking. Now you're leaving a proton. So instead of it creating water, you're creating chlorine and hydrogen, which is hydrochloric acid. So just remember, in the case if you do use a chlorinated system, if you use something like sebasoyl chloride, decane diol chloride, any acyl chloride is what these are called, you will create hydrochloric acid instead of water as your side product. And then going forward down here, remember to make sure to review the process of the reaction. And then, since we only did a portion of the answers here for the post-lab, make sure to review the portion that you had done there. Understand the condensation reactions, the step chain growth reactions, and then make sure additionally to note what your side product is going to be. Like the way that we discussed, is it going to be water, or is it going to be acid, like hydrochloric acid from an acyl chloride? So just make sure to also be able to identify and understand an IR and NMR spectra. There is a small portion up here that shows for this polystyrene that you can review. Additionally, it's NMR, but I would recommend to actually look at the data towards an NMR or IR spectra for nylon 610. And that's going to be about it for this section because it's kind of a shorter portion because this is more focused on the reaction itself. So I'm going to pause this recording, but then we're going to go forward into the next portion.